In the last lecture, we mentioned a few methods that could be used to resolve partial differential equations. And one of such we mentioned was the finite difference method. And then we considered the forward difference approximation, the backward difference approximation, and the central difference approximation methods for solving numerical methods for partial differential equations using the finite difference method. And now we'll consider a few more formulations, and afterwards we'll try to solve a few examples. So the next we'll consider is the finite element method. Now, for the finite element method, it literally involves dividing the domain into elements and using basis functions to approximate the solution. So if we consider the weak form of the partial differential equation, say the integral of du dx, dv dx, d omega, being the same as the integral over the omega domain, fv d omega. So in this case, v is referred to as the test function. And then the domain is discretized into elements such that the solution is approximated as u of x being the same as sigma I taking on values from 1 to n u sub I phi of I sub x. And in this case, we have phi of I sub s to be the basis function. And the resulting system of equations from the discretization process is then solved using the matrix method. And then another method we intend to consider is the finite volume method. And what the finite volume method does is to conserve fluxes across control volumes. So if we consider the conservation law, say du dt plus lambda, where that's to the gradient of f being the same as 0, then should we integrate over the control volume, that is, integrate control volume v, then we have d dt integral over v u dv plus integral f and dx being the same as 0. And once we discretize the integral over the finite volume, this will yield the approximation u sub I n plus 1 minus u sub I n over t plus f sub I plus 1/2 minus f sub I minus 1/2 over dx being the same as 0. So let us consider the spectral method. Now, what the spectral method does is to approximate the solution using global basis functions, typically the Fourier or polynomial expansion. So if we consider the partial differential equation du dt in the same as negative du dx, and this would be of the form du dt plus du dx being the same as 0, then by expanding u of st using Fourier series, that is u of st using Fourier series, then we have u of st to be the same sigma sub k u sub k hat t epsilon j kx. And in this case, one could substitute in the partial differential equations and then solve for the coefficients. So one more method will try to designate the formulation is the method of lines, MOL as you may call it. So what the method of line does is to discretize only the spatial variables, okay? So the method of lines discretizes only the spatial variables. And then it solves the resulting system using ordinary differential equations, you know. So once that is done, the resulting system of ODs solved using any of the numerical techniques. Okay. So for instance, if we should attempt to discretize the heat equation, we have du dt being the same as alpha d squared u dx squared, for instance. So if we use finite difference approximation, then we have du sub I dt being the same as alpha u sub I plus 1 minus 2 u sub I plus u sub I minus 1. Minus 1. This is 1 h squared. And once again, using the system, solving this discretized formulation, we get what is expected. So if we should therefore consider a simple example, so let's say we have u negative u prime prime, so that's a second order partial differential equation being the same as pi squared prime by x, for which x is an element of 0, 1. And then we have the initial conditions, u of 0 being the same as u of 1 being the same as 0. So for us to solve this, let's apply the finite difference method. So the first thing we want to do is to discretize the domain. And for us to do that, we already know that the interval is given between 0, 1. So we want to therefore divide this by n equal subintervals. So therefore, the step size h will be the same as 1 over n. Okay? And then we define the grid points. So if we define the grid points to be s of I being the same as I sub h, then I will take on values from 0, 1, 2, all the way to n. So for us to now approximate this second order partial differential equation at the interior points, so we're going to consider interior points S of I being the same as 1, 2, 3, all the way to n minus 1, since we already have this to be u of naught, and at this point we have u of 1, right? So n. So these are the interior points. So we'll now define the approximation within that. So u sub I of I sub x is approximately u of xi minus 1 minus 2u for xi plus u xi plus 1 divided by h squared. But in our case, we want to replace this by the negative, right? So this negative. So once we do that, then we are going to have, so this is this, and this would be the same as pi squared sine pi x. So this is now going to give us the negative of this expression, okay? So that we'll now be able to solve afterwards. Therefore, by convention, it means that u prime prime of x is the same as negative pi squared sine pi x, okay? So once we do that, so it means that this expression will now be the same as negative pi squared x. And then we can open this up such that this is now u sub I minus 1 minus 2u sub I plus u sub I plus 1 being the same as negative pi squared h squared sine pi x. So this must start being. So if we multiply through by h squared, then we have this expression. And now if we incorporate the boundary conditions, recall that u naught is the same as 0, and now un is also the same as 0. Then we now have that the unknowns will be u1, u2, all the way to un minus 1. So these are the unknown points. So we can therefore write develop the system of equations for that. So if we assume n to be 4, so let's assume n is the same as 4. So it means we have x0, s1, s2, s3, then x4. Okay, so it means we have 3 unknown points. So this is u0. So we have for un here. So we have 3 points in between. So we have to solve for u0. This u, let's be consistent, instead of x, then u4. So we have to evaluate for u1, u2, and u3. And so when we have I being the same as 1 for u sub 1, then we have 1 minus 1, that's u0, minus 2 u1 plus u2 is the same as negative pi squared h squared sine pi x. Okay, and this is u0 is the same as 0, so this is going to reduce to negative 2u1 plus u2 being the same as negative pi squared h squared sine pi x. Then when I is the same as 2, we have u1 minus 2u2 plus u3 is the same as negative pi squared h squared sine pi x. Okay, and this is another equation. So when I is the same as 3 for the third point, we have u2 minus 2u3 plus u4, okay, being the same as negative pi squared h squared sine pi x. Now, we already know that u4 is the same as 0, so this is now u0, and then this is now u4, right? So then it means that here we now have u2 minus 2u3 will be the same. So since this is 0, the same as negative pi squared h squared sine pi x. So in this case, we now have the system of equations so that u is the same as u1, u2, u3 transpose, right? And we already know that u1, for the first equation, negative 2u1 plus u2 is the same as negative pi squared h squared sine pi x1, right? Then that is, in this case, okay, let's move on. So we just wrote x in the previous, so since it's x of I, so x1, x2, x3, right? And in this case, we also have u2 minus u1 rather, the next equation will be u1 minus 2u2 plus u3 is the same as negative pi squared h squared sine pi x2. And then we also have u2 minus 2u3 being the same as negative pi squared h squared sine pi x3. So here we can now put up the system of equations where we now have negative 2, that's then 1, then u3 in this case is 0 for the first equation. Then here coefficient is 1, minus 2, 1. And here if u1 is 0, then u2 1 minus 2. So we have u1, u2, u3, which will now be the same. Now, negative pi squared h squared is common, so we can say negative pi squared h squared multiplying through sine pi x1 sine pi x2 and sine pi x3. So this system of equation could be solved, and then we get the solution accordingly. Okay, and then we can now consider the finite element method to solve this problem. So we want to first of all develop the weak formulation. So now I want to use the finite element method. So what we have to do first in terms of formulating the, or better still, expressing the weak formulation is to multiply the partial differential equation by a test function. So let's assume the test function in this case is v of x, okay? And now we already know that v of naught is the same as v of 1, for instance, based on the boundary conditions is the same as 0. So we are going to integrate over that boundary. So we now have negative integral 0 to 1 u prime prime of x, v of x, which is equation. The x will now be the same as integral 0 to 1 pi squared sine pi x v of x dx. So just multiply both sides and we've integrated. Now, afterwards, the next thing to do is to choose a finite dimensional space. So if we partition the interval 0, 1 into n equal elements, for instance, so we're going to have nodes x0, x1, all the way to xn, right? So the next thing is to use piecewise linear hard function, say phi of I of x as the basis function, for which I takes on values from 1 to all the way to n, to x, to n minus 1, being the internal points, right? N minus 1. So what we now have to do is to write the approximate solution to be of the form u of x being the same, or better still, approximately the same as sigma j being the same as 1 to n minus 1 u of j phi sub j of x. And we already know from the Galikins equation for each test function, then we now have that the integral from 0 to 1 will give us sigma, for which j is equal to 1 to n minus 1 u sub j phi sub j prime of x phi sub I prime of x dx will give us integral 0 to 1 pi squared sine pi x phi sub I of x dx. Now, this will give us the system described in the form sigma j equal to 1, n minus 1, u sub j, a I j, being the same as f sub I, for which I takes on the values of the internal points. Here, we also know that aij is the inner product, 0 to 1 by prime j of x by prime I sub x dx. And also f sub I is the same as the integral 0 to 1 pi squared sine pi x phi sub I of x dx. So this, we want to assemble this on a uniform mesh. So if we assume, say, n being the same as 4, just like we already described previously using the finite difference method, then for linear elements on the uniform mesh, then we'll find that the local stiffness matrix on the interval of length, say h, step size h, is given as k sub e being the same as 1 over h, for n being the same as 4 to be 1 minus 1 minus 1, 1. So if this is the local stiffness matrix, on a uniform mesh for n being the same as 4. So after assembling all over all elements and applying the boundary conditions, which will fix u of 0 to be the same as 0, and then u of 1 to be the same as 0, then the global system of unknowns, u1, u2, and u3, which are the internal points, will now also give us something as 1 over h, being the same as 2 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 2. times U1, U2, U3, which is the same as F1, F2, F3. And in this case, we can now tell also that each F sub I is computed via the quadrature. Okay, so there's a midpoint rule on each element here. And then we can also consider the finite volume method. And here we want to define control volume. So for each interior node, say S sub I, having elements of 1, 2, all the way to n minus 1, we define the control volume such that S sub I minus 1/2 and S sub I plus 1/2. So we also have that S sub I plus or minus 1/2 is the same as S sub I plus or minus H over 2. So the next thing will be to integrate the partial differential equation over a control volume. So we already have that negative U prime prime of X is the same as pi squared sine pi X. So we want to integrate this over the volume, negative integral S sub I minus 1/2, S sub I plus 1/2, U prime prime of X, the X being the same as integral S sub I negative 1/2, S sub I plus 1/2, pi squared sine pi X dx. So once we apply the fundamental theorem of calculus, we know that the left-hand side will be the same as negative U prime xi plus 1/2 minus U prime xi minus 1/2. Because once we integrate the second order, so we get the first order. And then afterwards, then we could evaluate to derive the system of equations and then solve. And well, now that we have done this, the approximation of the fluxes will therefore be done using the finite differences for the fluxes. And that will give us for this and for this, we now have U prime X sub I plus 1/2 will be approximately U sub I plus 1 minus U sub I over H, and U prime of X sub I minus 1/2 will be approximately U sub I minus U sub I minus 1 over H. So once we plug this in, then we are going to have minus U sub I plus 1, that's this, minus U sub I over H minus U sub I minus U sub I minus 1 over H is going to give us negative U sub I plus 1 minus 2U sub I plus U sub I minus 1 over H. So now that we have done this, we want to approximate the source terms. Now, we want to approximate the right-hand side by evaluating at the center. So the center at this point will now be S sub I, and then we multiply by the width, which is H. Okay? And once we do that, we are going to now have integral S sub I minus 1/2 to S sub I plus 1/2, that's the interval, pi squared sine pi x, the x will be approximately pi squared sine pi x of I h. So the finite discrete equation will now be the same as negative ui plus 1 minus 2ui plus ui minus 1 over h will be the same as pi squared sine pi x of I h. And once we multiply through by h, so once we multiply through by h, we're going to get u sub I minus 1 minus 2u sub I plus u sub I plus 1. So once we rearrange, right, this negative, so this becomes, this term becomes, yeah. That'll be will be the same as negative pi squared sine pi x of I h squared. And hence, we already know, since we have multiplied through by the negative, then we have the negative pi squared sine all of that. And now you see that this form is the same form we got from the finite difference method. So we just switch this position. So this is now positive. This is positive, and this is also positive. So we just switch them. So which is still the same. So we've not done anything different. So that's ui minus 1 minus 2u sub I plus u sub I plus 1 is the same as negative pi squared h squared sine pi x sub I. Okay, so technically what we just did here is that we have u sub I plus 1 minus 2u sub I plus u sub I minus 1 is the same as negative pi squared h squared sine pi x sub I, right? And this is positive, this is positive. So it's the same as writing u sub I minus 1 minus 2 u sub I plus u sub I plus 1 equal to this, okay? So that's what we just did. And now you observe that what we have here is the same as what we got for the finite difference method, and then the system of equations follows directly, and then we can pull up the solution. And then one more method we want to look up is a spectral method, okay? Here, the derivation of the system is done via the Fourier series. So for a periodic variant of what we are considering, so let's say uxs of x being the same as negative sine x, then over the interval 0 to pi, then with periodicity and periodic boundary conditions, we seek a zero mean solution. So we could represent this as u of x being the same as sigma k being the same as negative m to m u sub k hat e j k x, okay? And here, the series is truncated at some mode m, okay? So once we differentiate term by term, so the differentiation will give us usx of x being the same as sigma k being the same as negative m to m negative k squared u sub k hat epsilon jx, okay? So the Fourier coefficient equation we now become that is negative sine x will be the same as negative 1 over 2j epsilon jx minus epsilon minus jx from the convention, right? So we already know that from the trigonometric convention. So in this case, its Fourier coefficients will therefore be f1 hat being the same as negative 1 over 2j f hat -1 will be the same as 1 over 2j. And then f sub k hat will be the same as 0 for all k not being the same as plus or minus 1. So if we equate the coefficients for each k not being the same as 0, for instance, then we have minus k squared u sub k hat being the same as f sub k hat. So that for k being the same as 1, and also for k being the same as -1, we have u sub 1, u hat sub 1 being the same as f hat sub 1 over -1, which will be the same as 1 over 2j. And also for u -1 hat, we now have f of hat -1 over -1, which will be the same as -1 over 2j. So for all other k, if we now want to consider all other k, for instance, then u sub k hat being the same as 0. So also we set u of hat sub 0 to be the same as 0 to enforce 0 mean. And then we are now going to recover the solution by inverse Fourier transform. And that should give us u of x being the same as u hat sub -1 epsilon minus jx plus u1 hat epsilon jx. And this will give us -1 over 2j epsilon minus jx plus 1 over 2j epsilon jx. And this is the same as sine x. So now we can consider one more method, which is the method of lines. So for the method of lines, we're going to introduce some other constraints. So if we consider the heat equation, say u sub t being the same as u sub xx, then over the interval 0 less than x less than 1, then we have u of 0t to be the same as u of 1t being the same as 0, and also u of x naught to be the same as sine pi x. So the first thing we want to do is to discretize the spatial domain. Suppose we introduce n interior nodes. So then it means that the step size will be the same as h over n plus 1. Okay? And then s sub I will be the same as I sub h, for which I takes on values from 0, 1, 2, all the way to n plus 1. So the unknowns are therefore u sub I of t being approximately u sub s sub I t for all values of I being 1, 2, all the way to n, since we are considering n plus 1. Okay? So with this, we can now approximate the second derivative using the central difference approximation for u xx. So here we are considering the second derivative of the partial differential equation. So using the central difference approximation for u sub xx at the interior node, we have u sub xx x sub I t will be approximately u sub I minus 1 of t minus 2u sub I of t plus u sub I plus 1 of t over h squared. So the next thing is to write the ODEs, the ordinary differential equations. So the partial differential equations becomes a system of ordinary differential equations such that we now have du sub I dt will be the same as ui minus 1 of t minus 2u sub I of t plus u sub I plus 1 of t over h squared. And this is for the interior points 1, 2, all the way to n. Here we have the boundary conditions, u naught of t being the same as 0, and then un plus 1 of t being the same as 0. Okay? So the system is fully specified. So if we assume n to be 3, for instance, so if n is the same as 3, so we have S naught, S1, S2, S3, which is n, then we now have xn plus 1, S4. So with this, we already know for S naught, we have u naught of t already. And for S4, we have u4 of t being the same as 0, and this is the same as 0. So then we can now move on to resolve this, okay? So we can now estimate this for I being the same as 1, being the same as 2, being the same as 3. So the u1, the t will now be the u naught, 1 minus 1, minus 2 u1 plus u2 over h squared. So let us do that. So for I being the same as 1, we now have the u1 over the t being the same as u naught minus 2 u1 plus u2 over h squared. And this will give us minus 2 u1 plus u2 over h squared, because u naught and u4 is the same as 0 from the boundary conditions. Now, also for I being the same as 2, we now have the u2 over the t will be the same as u1 minus 2u2 plus u3 over h squared. Okay? And then for I being the same as 3, we also have the u3 over dt will be the same as u2 minus 2u3 plus u4 over h squared, being the same as, now u4 is 0, so this will be the same as u2 minus 2u3 over h squared. So we already know that the initial condition is given as u sub I of 0 being the same as sine pi x sub I, for I being the same as 1, 2, 3. So once the system is written in the matrix form, we have that du, the t is the same as au, okay? So in this case, we already know that a is the same as 1 over h squared. And here, what do we have? Now, this h squared, let's change the color. So this is 1 over h squared. So once we pull this out, it's going to give us 1 over h squared into bracket minus 2u1 plus u2, right? So here, this also will give us 1 over h squared into bracket u minus 2u2 plus u3 over h squared, right? And for this is also going to give us 1 over h squared, u2 minus 2u3. So 1 over h squared. Then for the first, we have minus 2u1, u2, the magnitude is 1. So let's remove the u. So that will give us minus 2. Then that's 1. Then u3 here is 0. So for the second, this is u1 here. So u1, that's 1. Then minus 2. Then 1. Then for the third, u1 is 0. There's no coefficient for that. Then u2 is 1. Then minus 2. So this is what we've got. So this can be solved using standard ordinary differential equation solvers. Okay, so well, analytically, we want to diagonalize A, and there we have to now find that the solution can be expressed in terms of the eigenmodes of the discrete Laplacian. Okay, and in a particular problem, the dominant mode corresponds to the eigenfunction that is in the discrete analog of sine pi x, right? So the idea is to now develop the exact solution. And for sufficiently fine discretization, then the numerical solution converges to these values. Okay, so I think that is it. So I would just mention a few things. When we also consider, I will just provide a formulation. Say we want to consider explicit finite difference method. Say the lax Wendroff, Leapfrog, and Upwind, right? Methods. So for the lax Wendroff method, we have u sub I n plus 1 being the same as u sub I n minus lambda over 2 u sub I plus 1 n minus u super n sub I minus 1 plus lambda squared over 2 u sub I plus 1 n minus 2 u sub I n plus u sub I minus 1 n. So in this case, lambda is the same as c dt dx. And for the leapfrog scheme, we have u sub I n plus 1 being the same as u sub I n minus 1 plus lambda u sub I plus 1 super n minus u sub I minus 1 super n. So this is the second order, but well, we can say well, second order accurate, but it requires an initial two-step solutions. Okay, that's a leapfrog. And then for the upwind method, so we'll consider the first order. We can now say that u sub I n plus 1 is the same as u sub I n minus lambda u sub I n minus u sub I minus 1 n. So this literally ensures stability for positive wave speeds, okay? So you could use this for the advection equation, okay? Now, there's one more thing that was described or talked about in the last class about the derivation of the Sylvester matrix. So I'll just quickly put that up. So conclude this note, okay? Derivation of Sylvester matrix. So, well, we say that the Sylvester matrix is a structured matrix that literally helps in determining whether two polynomials have a common root by computing their resultant. So here we have two polynomials. So in our previous example, we had a polynomial, and then we took the derivative to get the second polynomial. And the determinant of the Sylvester matrix gives the resultant, okay, and which is 0 if and only if the polynomials have a common root. So, okay, so now we want to derive the Sylvester matrix step by step. So given, say, the first polynomial to be the same as p of x, being the same as a sub n x super n plus a n minus 1 s n minus 1 plus all the way to a1x plus a naught. And then the second polynomial, in this case, we want to check for is bm s super m plus bm minus 1 sm minus 1 plus all the way to b1x plus b naught. So in this case, we say that p of x is of degree n and q of x is of degree m, right? Because that the degree is very vital in telling the order of matrix. If it's going to be a 2x2 matrix, if it's going to be a 3x3 matrix, or a 4x4, a 5x5, okay? So the two polynomials, p of x and q of x, have a common root, say alpha. If and only if there exists a non-trivial pair, say lambda mu, okay? Such that lambda p of alpha plus mu q of alpha will be the same as 0. And this will happen for all values of x, okay? Now, this leads to the system of linear equations in the coefficients, okay? And now we want to construct the polynomial multiplication system, okay? So here we say that multiplying q of x by powers of x, we multiply by powers of s up to n minus 1, and then p of x by powers of s up to n minus 1. So we could construct the polynomial system. So that is Sm minus 1, p of x, so we'll multiply through, will now be the same as an s m plus n minus 1 plus an minus 1 s m plus n minus 2 plus all the way to a1 sm plus a naught sm minus 1. The same applies. So we have s m minus 2 p of x will now be the same as an sm plus n minus 2 plus an minus 1 sm plus n minus 3 plus all the way plus a1 sm minus 1 plus a naught sm minus 2. So this will do all the way to p of x being the same as an xn plus an minus 1 sn minus 1 plus all the way to a1x plus a naught. So similarly, we do same for q of x, so that we multiply p of x by power of x up to n minus 1. So now, what we will now do is Sn minus 1 q of x will be the same as Bm xm plus 1 minus 1 plus Bm minus 1 Sm plus n minus 2 plus all the way plus B1 Sn, then plus B naught Sn minus 1. Then we have Sn minus 2 q of x being the same as Bm Sm plus n minus 2 plus Bm minus 1 Sm plus n minus 3 plus all the way to B1 Sn minus 1 plus B naught Sn minus 2. So we have this all the way to q of x being the same as Bn Sm plus Bm minus 1 Sm minus 1 plus all the way to B1 S plus B naught. So afterwards, we now set up the Sylvester matrix, and to check if P of x and Q of s have common roots, we now need a non-trivial solution for the linear system such that C1 P of x plus C2 Q of x has to be 0. So this is equivalent to solving a homogeneous system whose coefficients come from the Sylvester matrix. So the first m rows are found by shifting the coefficients of P of x in a Toplies-like manner. And then the next n rows are also formed similarly with the coefficients of Q of x. So the Sylvester matrix S PQ will now become something like an minus 1 all the way to a1, a naught, 0 all the way to 0. Then we have 0, an. Then here we have an minus 1 all the way to a1, a naught all the way to 0. So we now have this going down, right? So we have all zeros here. Then we have an minus 1. We have a1, a0. So we have bm. Then we have bm minus 1. Then we have b1, b0. We have 0, 0. Then we have 0. We have bm. We have on this, we have bm minus 1. Then we have b1. We have b0 all the way to 0. So this continues all the way to 0, 0. Then we have bm minus 1. Then we have b1, then b0. So this gives us the Sylvester matrix derived. So the first m rows comes from P of x, each shifting the coefficients to the right. Then the last n comes from Q of x, similarly shifted. So the determinant of the matrix is called the resultant, okay? And by interpolation, if the determinant of SPQ is 0, then it means that P of x and Q of x have a common root. And what if the determinant, so let's say determinant. What if the determinant is not the same as 0? So what if the determinant of SPQ is not the same as 0? Then it means P of x and Q of x have no common root. So now we'll consider P of x being the same as a sub 2 x squared plus a1x plus a0, and Q of x to be the same as b3 x cubed plus b squared x squared plus b1 x plus b0. So in this case, the polynomial P of x have degree of n being the same as 2, and then Q of x have degree, polynomial degree m equal to 3. So this is going to give us m plus n rows and columns for the matrix. So in this case, we have 2 plus 3, which would be a 5 by 5 matrix. Okay? So that's m plus n rows and m plus n columns. Now, since P of x is of degree 2, so we are going to have P of x, we now have m rows, while Q of x, we have n rows. There's a swap. So it means P of x, we have 3 rows, while Q of x, we have 2 rows. And then we can now do this. So A2, A1, A0 is 0, A2, A1, A0. Then 0, 0, A2, A1, A0. So that's that for the first. So it has 3 rows. It takes the polynomial degree numbers for its rows. Then Q of x will now have n rows. So that will be B3, B2, B1, B0, 0. Then we have 0, B3, B2, B1, B0. That's that. So we have We now complete that. We'll complete this and complete this. You see that the Sylvester matrix is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 gives us a 5 by 5 matrix.